Okay. Mm, oh, we so, par, I will check my questions and I will share my screen. So please
Sure.
wait a minute. Thank you.
Yeah, no problem. Thank you.
Mm, So I want to. Uh, Drama.
Param.
Para. Para. I had the quick questions about loan
Okay.
regression, and
Okay.
in the quote marks, the Xingang give us some example test, and
Okay.
I find a question about interprets the coefficients of the loan, and
Okay.
someone is a loan, and someone is original data, and someone
Mm-hmm.
is loan minus the original data. How to interpret the coefficients, because I think it's many data. So how to use one sentence or the uh I mean some sentences to
Mm-hmm.
interpret. Yeah.
Okay. So let's see. For example, we could have something like, say, y hat
Mm-hmm.
is b0 plus b1 times x1,
Mm-hmm.
and it could also be, say, b2 times, say, log of x2, right?
Mm-hmm.
So we could have scenarios like this. Does it make sense?
Yeah.
Yeah. So then we ask ourselves, what does b1 represent, right? So we are saying if x1 goes up by 1 unit, then y hat goes up by b1 units, right? So this is what we know about this coefficient. And again, this is assuming everything else is the same, like x2 doesn't change and so on, right? So we already know this part. Now we ask ourselves, what happens if everything else is same but x2 changes, right?
Yeah.
So here what we are saying is, if x2 goes up by 1 unit, what happens to y? So that's the interpretation we have of b2. And remember, we could say that if log of x2 goes up by 1 unit, then my final variable goes up by b2 units. But again, from a management perspective, log of something going up does not make a lot of sense, right? So in that scenario, we would then say that if x2 goes up by 1%, right? So for x2, we will use the percent concept, whereas for x1, we will use just the number concept. Does it make sense?
Uh, actually, I had a B3, the lower
Okay.
X3, minus X4.
So B3 of,
The loan X3, minus
yeah,
X4. how to explain this one?
Okay. So one simple thing you can do is, in that case, you can just expand it out. So
Mhm.
this basically says this is b3 times log of x3
Mhm.
and plus, I would say, negative b3 times x4. Does this make sense?
Okay.
So if you just expand this out, this is what you get. So in that case, you can make the same inference. If x3 goes up by 1%, how does it impact the final variable? And if x4 goes up by 1 unit, then this is negative, right?
Mhm.
So for example, if this number was, let's put some numbers here. So let's say this was maybe sales is equal to, say, 3 times maybe log of hours
Mhm.
minus, let's say, let's put something in, say log of hours minus, say, leaves.
Mhm.
Okay, so in this case you can just expand this, saying this is 3 times log of hours minus 3 times leaves, right? Or it is same as plus negative of 3 times leaves. So then you can make you can sort of give the interpretation that if hours goes up by 1%, then sales goes up by that same thing. You have the 3 divided by 100 kind of thing. So that's one part. And leaves, you can say if leaf goes up by 1 unit, then sales goes down by 3 units, right? Because this is negative 3. Does it make sense?
Yeah.
So if you just expand it out, then you can use the same rules that we have done earlier, whether so this side could be log and this side could be log or not log and so on.
So you mean if the two data, one is log, one is not log, it multiplies. Also, we can separate these two to part.
Exactly.
Okay.
Right.
Cool.
Right. So it could be the same thing. Like for example, if you say that, say, y hat is 2 plus, say, 2 times x.
Mm-hmm.
So this is same as saying it's 2 times 1 plus x, right? So it's just using algebra, nothing more. Does it make sense? So in that case, you can just expand it out and then make the interpretation the way that we have done earlier for log linear or linear log or log log. Does it make sense?
Yes, clear. And
Okay.
and how to interpret the interaction? Yeah, how to interpret the using sorry, it's such as we use the interactions in one model, and how to interpret and this advantage or the limitation about the interactions.
Okay.
Yeah.
So let's think about that. Let me maybe add. I'll see if I can add another whiteboard. Oh, okay. I have to just use this. You know what? Let me just move this out a bit.
Okay. Thank you.
So when we are trying to do interactions, basically we are trying to say it's something like y hat is b0 plus b1 times x1 plus b2 times x2, and then we're adding a third term which is b3 times x1 and x2. So this, when you have, so this is the interaction term where we are multiplying the two things together, right?
Yeah.
So in that case, let's ask ourselves, what happens if x1 goes up by 1 unit? So that's the key thing we're trying to understand. So if x1 goes up by 1 unit, you can see what's happening here. So this is becoming b0, and then my b1 goes up by 1 unit. So I know that part. That's pretty clear. And then there is also an impact. If x1 goes up, then this is the additional piece that is happening, right? So this is same as saying this is b1 plus, so this is same as b1 plus b3 times x2, right? So this whole thing multiplied by x1. So that's the key message we get here. And then there is this sort of regular term. So then what we are saying is, if x1 changes, the slope is not only dependent on x1, but the slope is also depending on x2. Does that make sense?
Mm-hmm.
So effectively what we are saying is, instead of just assuming that, let's say this is the slope that I can say is based on x1, right? So if let's say this was x1 and y hat, so instead of just saying this is the slope, which is b1, I'm now having a different slope, and I'm saying the slope itself depends on x2. So that's the key message when we give an interaction term. So then what we're saying is, if x2 is changing, then potentially my slope itself can change. So let's try to put some terms around this. So let's assume that x2 is a binary variable, and it is, let's say, 0 or 1, depending on, let's say, it's male or female. Okay.
Mm-hmm.
Then what's happening is, if my x2 is 0, which means it's a male, then my equation simply changes to y hat is b0 plus b1 x1, and I know that x2 is 0, so this goes away, and x2 is 0, this goes away. So there's no interaction term that is coming for male, right? So this is the equation for males. Now what happens when your x2 is 1, which means it's a female? So in that case, you can see that your equation will change to y hat is b1 times x1, which is this part, and then your x2 is 1, so you add an intercept, which is your b2, right?
Mm-hmm.
And because your x2 is 1 here, then you have this extra term, which is b3 times x1. Okay, so in effect what happened is, when it comes to female, there is an impact on the intercept, which is b2, and there is also an impact on the slope, which is now becoming b1 and b2 together. So how do we interpret this? If, for example, we had data like this, which is, say, x1, and we want to say, how does it look for, let's say, male? So this number would be something like, this is my b0, and this slope is b1. So this is how it works for male. Okay. Now, if I change it to, let's say, female, then first there is a gap. So it starts at a different point, which means this is now b0 plus b2. So this is my intercept part. So I should have added b0 here. So this is my b0 plus b2. And now the slope is also different, because now the slope is something like b1 plus b3. Does this make sense?
Yeah.
So this is how it works for female. So in effect, what the interaction term is doing is, it is saying that my slope is not same for everybody, but my slope is different based on another parameter. In this case, let's say we said x2, which happens to be gender, that influences the slope. So that's the key message you can think of what interaction is bringing to you, saying that there is some impact on the coefficient, which is what this one is doing. This part is doing is the impact on coefficient, but there is also an impact on the slope itself, which is what this piece is doing, right? So that is the key outcome that you would normally see in interaction. So usually when you look at these sort of images, it's like this regression, when you take a look at, so normally what you might see is, if you don't look at, so if you don't actually consider this male part and so on, so you may possibly see data that is spread out like this. That is spread out like this, right?
Mm-hmm.
And this tells you that looks like I'm not having data that is sort of falling on a proper line. Okay. And in general, what will happen is, even if you try to fit a regression without considering this impact, when you plot the residuals, right? Your residuals might possibly have small initially, and then as the number changes, the residuals might also increase. Do you see that point?
Yeah.
Now this tells you that looks like there is some pattern. Now the moment you look at this data and then you realize, let's find what happens for male versus female, you will then see that most of this data seems to be for male, whereas most of this data seem to be for for female. You see what I mean? So this tells you that it is not just one simple equation, but looks like there are two different equations based on male versus female. Does this make sense?
So you mean some factors such as the B2 and the B3X2 will impacts our model. If our model is only focused on the male, but so if we check the female, it will give us different results or the outcome. So
yes, you're right. Yeah. So usually this is, so see, you don't start with interaction, right? You first start with a simple linear regression, and once you build the regression and you see that some of your assumptions are not getting validated, like in this case the homoscedasticity is missing, then you will look for more information saying that does there seem to be a different pattern? And then when you do more analysis, you will then realize that, oh, looks like this particular group or this particular line that I'm seeing is more relevant for male, and this particular line is more relevant for female. And that tells you that looks like being male or female has an impact on the slope itself. Right? So that is when you will realize that, oh, my slope itself depends on one of the parameters, which means this is a possible case of interaction. Right? So in sometimes, again, depending on the data, you may also have a completely different trend. So it could be, so it could be something like, let me just move this a bit. So for example, you could have data that looks somewhat like this, and then you also have this scatter that looks somewhat like this. So in general, if you look at this, you might possibly see that the correlation is almost zero, because there is an equal chance of something being high or low. So you can't say that if X increases, does Y increase or decrease? Because looks like it is increasing or decreasing at the same time. So when you see graphs like this, it possibly tells you that looks like there is some other factor that will give better explanation. And usually, again, if you, for example, there is some scenario which says that for male, the slope is positive, but for female, the slope is negative. Do you see what I mean? So in that case, you might possibly see that this is a different curve for male and this is a different curve for female. And that will again give you an interaction term. So in this case, your interaction term might even be, say, negative. Your B3 might be negative, which means that for male, possibly this is a positive slope, but for female, it ends up being a negative slope. Right? So when you have patterns like this, where you see that based on, say, one of the variables, the graph seems to be sort of distinctly different, that could be a good case to see, should I consider interaction as one of the terms or not? Does it make sense?
Actually, I feel the confusing about you said male and female, because if we use dummy variables about male or females, we need to delete one, so we can't see the only two dummy variables. The total number of the two dummy variables in the same model. So why we can get the different dummy variables models in one graph?
Okay, so when you say two dummy variables, so for example, if you remember, one of the things we did in the tutorial was the sales based on male versus female and training versus no training. Do you remember that part? So it's like, so there's one dummy variable saying whether it's male, yes or no, and another dummy variable saying whether it's training, yes or no.
Yeah.
Okay. So in that case, effectively what we're saying is it's not just the male, but it's also the training which has a possible impact. Right? So in that case, let me just clean this up. So if I remember, in that case, we did something like, say, sales is going to be equal to B0 plus B1 times whether it's, say, male or female. So I'll just put male here, saying it's 0 or 1, plus B2 times whether it is training, yes or no. And then let's say there was some other term. Say this was maybe the number of hours and so on. Now we realize that there is an impact of male and there is an impact of training. But we also see that the impact of training is different on male versus female. Okay? And that's when we added another term. Let's say we call it B4 times male times training. So now let's see what happens when it happens to be a male. So when it was a male, we would say it is B0 and this would become 1. So it will say B0 plus B1 and this term would also be there. So I will also have say B2 times training plus B4 times training plus my B3 which was hours and so on. Okay. Now on the other hand, if it happens to be a female, then I will simply have B0, then this term goes away because my male is 0 and this term also goes away. So I would simply have this plus B2 times training plus B3 times hours. So this is the model for male versus female. Okay. Now what this is telling us is that for female, if training is provided, this is the impact. Whereas for male, if training is provided, this is the impact. Do you see the difference?
So it's more a B4. Yeah.
So now if we talk about, let's say, male with training, then this T becomes 1, right? This training is either 0 or 1. Oops. So in that case, if male is with training, then we can say this is B0 and B1 plus B2 plus B4 and your hours and so on, right? Whereas if it's a female with training, then this becomes B0 plus B2 plus B3 times hours. So do you see a difference between training for male versus training for female? So female training is increased by this amount, whereas male training is increased by this amount, besides this one which is already based on male or female, right? So this is an additional impact that you see which is happening for training which is given to males. Now if it's a male without training, in that case the T becomes 0. So then you would have something like B0 plus B1 plus B3 times hours. Whereas if it's a female who is untrained, it simply becomes B0, your B2 goes away, plus B3 times hours. So if training is not provided, then this term is anyway not relevant. Then the only difference is the coefficient for male versus female, right? But if training is provided, then there is an additional impact of this combined term which is not applicable for female but only applicable for male. Does this make sense?
Okay. Yeah.
So in effect, when we are talking about interaction terms, what we are saying is, yes, there is an impact, but the impact changes based on another variable. Okay.
Sorry, what?
So what we are saying.
Sorry, what? So, I feel confusing about impacts about other variables. What's mean?
Okay. So for example, we said, yes, training has an impact on sales. Does it make sense?
Yeah.
So yes, we agree that if training is provided, sales goes up. So yes, training has an impact on sales. But we are also saying, but the impact is different for male and female. So it's not the same impact. So if we did not have this particular term, if we did not add this particular term, then we would just have this B2. Then what we are saying is, if I provide training, sales goes up by 5,000. But then when I do more analysis, I realize that no, sales doesn't go up by 5,000 for everyone. Maybe it goes up by 4,000 for male, but it goes up by 6,000 for female. So then it is telling me that the impact of sales is also dependent on another variable, in this case, gender. Do you see the difference? So when I'm saying there is an impact of one variable, but the level of impact depends on another variable. So which means the two variables interact with each other to sort of quantify what is the impact of that particular variable. Okay. Does this make sense?
Yeah.
So that is when you say that there is an interaction term, because the impact of one of the variables is dependent on another variable.
Okay, I see. So, could I repeat your words again if you
Sure.
check my thought is clear. So you mean when we use interactions, we can find some other variables would have the positive or negative the impacts to our test or the other variables test. You mean that? It's clear.
Yes, the only thing I will add is the impact of variable 1
Mm-hmm.
itself depends on variable 2. Right? So the impact of training depends on gender. So training does not depend on gender. So let's make that very clear. So there may be no correlation between training and gender.
Mm-hmm.
So what this means is I provide training to maybe 50% of the females, I provide training to 50% of the males. So in general, what we are saying is training and gender are not correlated. So I can't say that I mostly train females or I mostly train males. So I don't have any correlation between the two. So is that part clear?
Yeah.
So there is no correlation between gender and training. But there is an impact of training, right? Which is what my coefficient talks about. So if training is 0 or 1, then the sales is up or down.
Mm-hmm.
But the impact of training itself depends on the gender. Does this make sense?
Yeah.
So I think what you explained is clear. The only last part that I would add is the impact of variable 1, that impact itself depends on variable 2. Although variable 1 does not depend on variable 2. But in the regression, the contribution of variable 1, which is the coefficient, that depends on variable 2. So that's the key message to keep in mind.
So that's its limitation about in interaction. But the advantage of the I don't know the advantage of the interaction.
So I would say the advantage of interaction is that it helps you explain the model better. Like for example, if we just go back to this scenario, where if I did not look at the interaction of say the gender on a particular slope or one of the coefficients, then I would most likely get a number that is somewhat like this. So maybe I will say that say sales is equal to whatever, say 500 plus say 200 times say hours. Let's say I come up with this kind of a number, not realizing the fact that if I use gender, I can possibly explain this better, right? Because if I use gender as one of the interaction terms, then possibly I can explain this better. So I think that's the key message we lose out if we don't use interaction. So when the impact of one variable depends on another, if you don't capture that, in that case, most likely you will see that your degree of fit, like your adjusted R square, is usually on the lower side. Some of the variables are not really having significance in terms of the p-value not being low enough. But the moment you add the interaction term, you might see that your adjusted R square goes up significantly. And your homoscedasticity is then maintained, because then you're already having that in your prediction. And then when you're comparing your error to your value, you will possibly see that it's more uniformly distributed rather than being sort of either going up or down or not meeting the homoscedasticity assumption, right?
Yeah.
So in effect, you will see that in those scenarios, your adjusted R square will usually go up and your p-values will usually go down for all the relevant variables and interaction terms. So the advantage of interaction would be that it makes your model better. It improves the statistical significance of your model, right? And it helps you meet some of the assumptions of regression, which is like it usually improves the homoscedasticity of the overall distribution. Does it make sense?
So you mean the advantage of the interaction is makes the model makes the model better, and the such as the coefficient will increase, and the p-value will decrease, and
sorry, see the coefficient may not increase or decrease, so that we
Okay.
don't know. The coefficient may change, but the significance f will go down, the adjusted r square will go up, and the p-values of the relevant variables should go down. Does it make sense?
So the significant f and the p-value will go down, and
Yes.
and so we can more clear to explain the relationship with dependence variables. Yeah.
Yes. you're
Okay.
right.
Cool.
And again, this is assuming that you pick the good interaction terms.
Mm-hmm.
So if you just add some interaction terms, whereas when there is no real interaction, in that case your model may even get worse. Do you see what I mean?
Yeah.
So if you try to say that training is related to gender, but it's actually not related to gender, you would most likely see that the p-value is not is like above your cutoff limit, and most likely you're adding more variables, but it's not improving the explanation, right? In which case your r square may go up a little, but your adjusted r square will start going down.
Okay, cool.
Yeah.
And I have another question about I feel the confusing
Okay.
about sorry, I will check the question. I will want
Okay,
to
sure.
to ask more clear the question.
Okay.
I will check.
I'll just clean this up so you can use the whiteboard.
Thank you so much. It's so clear.
No problem.
Yeah. Answer my questions. What's my question? Actually, I use logs in our final presentation. You see the log can makes the variables the data to be the normal distribution. It's one of the advantage about log. And do you have the other advantage of the log?
Yeah, so what you pointed out is very right. So usually if the data has a right skew, it tries to make the log sort of makes it a little more normal than it was. The other advantage of log is what earlier might be seen as an outlier. So once you do a log, it's no longer an outlier, right? Because if you remember what happens in case of outlier would be, let's say you had data like this, say something here, and then say this one goes way up like this, right? So let's say this is your y variable, and even if you have two choices. One of them is you ignore this, then you get a line which is having a good fit, right? But in this case you have actually ignored this data altogether, so that's again a big risk. So if the data was properly collected, we ideally should not ignore it. But on the other hand, if you say that, okay, I don't want to ignore it, then what option do you have? You have something like this. So you build a line that looks like this. Now, this is the best line you can fit if you want to include this outlier. But what happens is, again, you can see that the line fit is going to be very, very poor. You see what I mean?
Yeah.
And the other challenge you might have is in terms of the distribution of the errors. You might possibly see initially the errors are positive, then it goes high, negative, then again it goes positive. So it's not going to have the uniform distribution of errors. Now, if you take this same data and then you try to apply your log to it, so one of the things that log does is all the extreme values will start sort of coming down, right? So this part will sort of get squeezed when you do the log. So in which case, you might possibly have numbers in this point will now possibly come somewhere here. So it may not be as much of an outlier once you do a log. And in that case, you may possibly have a much better fit rather than having this really bad fit you were having earlier. So besides making the data more closer to normal, it also reduces the possibility of extreme outliers.
Yeah.
Does it make sense?
Yeah.
So those are two things you can think about when you try to apply log to any of the variables.
So I repeat your words. It means if because in our model we sorry, it's not model, in our data we random data, we can find some outliers. Some outliers will impact our regression model, it makes the regression model more higher or the lower. So if we use a log, we can find the outliers and we can reduce the outliers the impacts of the
Yes.
outliers to the regression model and
Yes,
make
I think that's
makes the outliers more close to the regression model.
yes.
Does
I
it
think
mean?
that's a very good interpretation. Yeah. So it reduces the impact of outlier on the quality of your model. You're right.
And I had another question. It's I will check my question table because I have the many questions makes a questions table, but I think some questions is the same topic, so I want to
Okay.
reduce your time.
No, that's okay. I
Okay.
have time till, I think we are here till 1 o'clock, so that should be okay.
Okay. Thank you so much.
No problem at all.
Uh,
I just try to erase this out. So
I find interesting questions.
okay.
Oh, the one of the question is how to check the left skin. The left skin. I use the mean the location of the mean and the medium and mode to check the data distribution is skin is left or right. It's right or not?
Yeah, that's definitely right.
Uh-huh.
The other thing you can do is if you have the descriptive statistics, you also have something called skew in the descriptive statistics. I think it will write like skewness. And if it's a normal distribution, this will be 0. And if it's like a negative or a left skew, then this will be negative. Or if it's right skew distribution, like this one, then this skewness will show positive. So you can look at this, which is in your descriptive statistics, or what you said is very right. So in this particular case, if this is your median, then your mean will be on the lower side, right? And in this case, if let's say this is your median, then your mean is going to be on the higher side.
Okay.
So you can use both the scenarios to identify this. The only thing I would say is if you have data that sort of looks like a good distribution, then you can use the rule that you said, mean and median. But let's say you have data that looks far more, it's not really following a pattern, but it looks something like this, and then it has something like this, and then it has something. So if you have data that's not really following a nice skew pattern that you see, in that case, descriptive statistics will be a little more reliable. You see what I mean? So if you have data that clearly has a pattern like this, then what you said is a perfect option to just see whether the mean is higher than the median or not.
Okay. So if the question is so you mean if the question is to check the skewness, so first we can use the to check the descriptive analysis, check the skewness. If there is a negative, we check we think this was left skewness, and and there is a positive, it's the right skewness. And the second we use the medium. If the medium is in the right of the mean, so it's it's left. If the medium is in the left, so it's right skewness.
Yes, you're right.
Cool.
Cool. So you can use both these options to do it. So depending on how the distribution looks like.
Because I feel confusing about these questions because in the it's a lecture the week 10 the Xinggang says one sentence is about the mean the mean can lower than the minimum data. Yeah. So I feel the very confusing about this sentence.
Can you repeat that statement? The
So
mean can lower?
the mean can lower than can be lower than the the minimum data.
Mean can be lower than the, yeah. So
The
for example,
medium-
in this case,
Yeah.
if you have this as the median, so here the mean can be lower than the median, right?
But he says minimum data, the smallest data. I feel very
I think he must have meant median. Maybe it was maybe not spelled properly, or it was not.
Oh, okay.
Was it in the slides or was it in his lecture?
In the lecture.
Yeah, I think that must have been maybe either he misspoke or there was a confusion. But yeah, what he meant was the mean is less. Yeah, how can the mean be less than the min? That's not possible.
So I feel very confusing. Maybe it's my mistakes about the listening.
No, yeah, I think maybe, yeah, that's usually a problem when you have these recordings and all, right? It may not be as clear. But yeah, I think what he meant was the mean can be less than the median, which typically happens if the data is skewed.
Yeah, so clear. And and another question. Yeah. So, because in the example, the simple test in the CloudMark, I find the questions about it's open questions. So Xinggang will give us such as the mean, the median, the standard deviation, the standard error. No, not standard error. It's a mean, median, standard deviation, and so you can check data table such as the squared data to calculate the standard error. And so we use mean, median, standard deviation, and standard error to explain the data distribution, and the such as I will give the example. It's look like the oh yeah. Do you see the example of the sample test in the CloudMark?
I don't think I have access to that, but let me do one thing.
Okay, I will share the screen.
Let me just let you share the screen.
Yeah. I will share the screen of the comment.
Yeah, you should be able to share it now.
Okay. So wait a minute. I will find the.
Yeah, that's okay.
Actually, okay. It's my memory about past test. Sorry, because it's a similar of the simple test. So I mean so so the first one, so we need to explain the difference about the standard deviation and the standard error. This question I know the answer, and this open questions for me, because I need to focus every part, such as mean we need to answer the average, the medium we need to, such as Xinggang said, if we pick up one worker or one data, you can find it's more likely to pick up the medium data, and or the mode data. And
that's the mode.
The mode. Yeah.
The most frequent.
Yeah, how to explain the medium?
So so when you look at median, so what we're talking about is median is the point that you have 50% of the population below and 50% of the population above. Okay, so when I say that let's say the median height of the class is, let's say, 160 centimeter. Then if the class has 100 students, then I know that 50 students have more than 160 and 50 students have less than 160. So you can think of median as the point that splits the data into two groups. Does it make sense?
Okay.
So if let's take the example of, let's say, salaries. So if you say that the New Zealand median salary is, let's say, 55,000.
Mm-hmm.
So what that means is half of the population earns less than 55,000, half of the population earns more than 55,000. But it is possible that the ones who earn more than 55,000 earn far, far more. Like, for example, somebody could be earning even millions, which means that your mean might be more than the median. Do you see what I mean?
Yeah.
Whereas on the lower side, it can't be less than zero. Like, nobody will earn negative, right? So when you say the median is 55,000, all you're saying is that half of the population earns less than this, half of the population earns more than this. Does it make sense?
Yeah.
So you can think of, so when you're trying to explain median, so that's what effectively you're saying. So if you say, for example, the median marks was, let's say, 85%. So all you're saying is half of the students got above 85, half of the students got below 85. So that's the interpretation for median.
Okay. So so you mean if we use the median, we find the median can divide its two group. The one group is less than the median. The another group is larger. So we pick up the data. We can find the two groups. It means
it will be two equal groups.
Okay, two equal.
Like,
yeah.
Yeah. So
okay.
Because both. So as I said, if you have 100 students, so 50 students have height above 160 and 50 students have height below 160.
Okay.
So it's splitting into two equal groups.
Okay. So, and I find another questions about regression interpretation. So, the question is so my question is for, because the regression we can use coefficients, the multiplied R, and adjusted R square, and the significance F to find the model. The regression model is acceptable, and so we can find the coefficients and the p-value to check the independent variables. It's has strong relationship with others, and its p-value we can find it's acceptable. Could you give me some more such as more efficient information to interpret the regression model rather than me just for...
So I would say definitely adjusted R square makes a lot of sense if you have, say, multiple variables. If you have a single variables, then R square is good enough. But for multiple variables, yes, adjusted R square, especially when you're comparing different models. So let's say you have one model which has maybe, say, gender and number of hours. Another model has, let's say, age and number of hours. And maybe a third model has age, gender, and number of hours. So when you're comparing different models which have different number of variables, their adjusted R square makes a lot of sense, because adjusted R square sort of adjusts for the number of variables in the model. And the other thing is, when you're looking at the coefficients, so yes, we definitely want to look at p-value, because p-value tells us the statistical significance. But we also want to look at the coefficient itself, because if the coefficient is extremely small, then there is a statistical significance, but there is no business significance, right? So let me sort of give an example of that. Let me just try to share my screen. So let's say we end up with an equation that looks like this. You have y hat is, so let's say we're trying to predict sales. So we're saying it's 5,000 plus, let's say, 30 times the number of hours worked, plus, let's say, 500 times whether it's a female. So let's say this is a binary variable.
Mm-hmm.
And let's say I have a number like this. It's 0.0025 times, let's say, whether the person wears a ring or not. Okay. So let's say some people have a habit of wearing rings, some people don't have a habit of wearing rings. So let's say this is a variable which just says whether the person wears rings or not. And for this coefficient, maybe the p-value is something like 0.0001.
Mm-hmm.
Right? So all that is telling you is that this coefficient is very unlikely to be 0. But if you look at the value of this coefficient, this is so small that even if it is statistically significant, it does not really mean anything. So all you're saying is, if I know the person wears a ring or not, I can tell whether the sales went up by maybe less than 25 cents. So it's not even a cent. Do you see what I mean?
Yeah.
So I think that's another thing to sort of comment about, that the coefficient may be statistically significant, but it may not have any business relevance at all because it's so tiny that it does not actually add a lot of value. And a lot of times you may also look at what is a variable that is being used. So let me then change this to something like, so let's say we say this is not relevant, so maybe we can just drop this. So here we said it is 30 times hours, right? So if I try to change it to something like, say this could be as small as 0.00012 times, say, seconds.
Mm-hmm.
So in this case, what's happening is I'm putting the independent variables as, say, number of seconds the person was working. And that's the reason the coefficient is very, 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 very small.
Mm-hmm.
But that's not really helpful, right? So I should also pick the right units for my independent variables. So if I pick the unit as hours, it gives me a much more relatable coefficient, which actually makes sense. So I can say every hour he works, he produces $30 more sales. So these are some of the things to look at. What is the unit I'm using? Does the coefficient make a lot of sense? Even if the coefficient is statistically significant, does it actually help me in taking business decisions? Right? But foremost, I would say you should look at what is a basic theory. So do you think it actually makes sense to say that if you work more, your sales will be higher? So it sort of logically makes sense. There is a lot of business theory behind it, right?
Mm-hmm.
Similarly, you can say that gender has an impact on sales. So depending on a particular industry, maybe male are likely to sell more or female are likely to sell more. So yes, you can say based on your knowledge of the industry and based on your business understanding, yes, it may have an impact. Now, whether somebody wearing a ring, does it have an impact on sales or not? There is absolutely no theory behind it. You may be just curious to know about it, but it does not seem to make any sense, right? So you have to first start with, what do you think is a good business explanation for this variable, and use that to sort of drive your regression model. Does it make sense?
Yeah. So you mean the so we can add more information about the coefficient if the coefficient is it's too low, so too small. So we can think this coefficient is not to effectively impacts to on the dependent variable.
Dependent variable.
Yeah,
yes,
dependent variable.
Yeah. That's a fair conclusion.
And I find an interesting question about in my final presentation, because in my final presentation I check the total cases, and I think I use a log to make the total cases to be the normal distribution. But I checks it's a similar I had this the final presentation. The question is similar as the sample test. One question it means if the data it's not a normal distribution, what problems in your model will happen, or we can could we use the data without the normal distribution? And my second question is if we use the log to make the data to be the normal distribution, but I use the log, but I find the log data is also not to be the normal distribution.
Yeah.
So
Yeah.
so it feels very confusing. So how to explain or how to
Yeah. So what you pointed out is something that would happen in real life. That log is not the answer to all the problems, right? So a lot of times, sometimes you do log. There are some scenarios where you do square root or even cube root. So there are different transformations. Again, that's not part of the course, so don't worry about that. So there are different transformations that can be applied to try to make sense of the data and make it normal. The log makes a lot of sense because log is something that applies for most of these, say, financial numbers or things which typically have a significant right tail distribution. Their log makes a lot of sense. Now, in this particular case, this is not a fabricated data. This is like real data that Singa has downloaded and given you. It is very hard to really expect that the log will be perfectly normal. So it is very much likely that the log is not normal as well. However, what we need to make sure is we build the model and we make these assumptions very clear. So we put the possible limitations. So all you're saying is, because the data is not perfectly normal, therefore there is a possibility that I'm making a mistake in this model. So that's the key message that you're sharing. If your assumptions are being met, so if you look at regression foundation is that your errors must be normally distributed. So again, keep in mind, the assumption for regression is not that the data must be normally distributed, it is that the errors must be normally distributed. Okay? So it is possible that the data is not normally distributed, but maybe you used a non-linear function, like for example, you used an interaction term, or you used a quadratic term. So these, or you used a log term. So this will make sure that your data may be not normally distributed, like your data may have a skew, but your errors are getting normally distributed. So if you look at the assumptions for your regression, the error terms should be normally distributed. Do you remember that 4 rules you have for the 4 assumptions for regression?
Yeah.
So it is not saying the data must be normal. It is saying the errors must be normal. Right? So usually if the data is normal, the errors will also be normal, or at least as close to normal as you can expect. However, when the data is not normal, then it depends on how you have modeled your regression. As I said, if you use a quadratic term, that might bring your errors back to normal. Or if you use an interaction term, that might bring your errors back to normal. Or if you log one of the variables, it might bring your errors back to normal. So there are different techniques you can apply to bring your errors to normal. Does it make sense?
Excuse me. I lose my direction.
Okay.
I lose.
Okay. So let me put it this way. Okay. So let me just clear this up.
Yeah, thank you.
Just write it here. Yeah. Okay. So let's ask ourselves, what do we do? What is the assumption? So the assumption is that errors are normally distributed.
Yeah.
Right? So if we find that the errors are not normally distributed, what are the possible options we have? One of them is we can try to log it and see whether that helps. Or the other option we can do is we can try to fit a quadratic term. Right? So if you remember, if we have data that sort of looks like this, so we see that if you try to fit a linear one, it's not going to work, in which case it's better to fit a quadratic kind of scenario. So that's one scenario. The other one is to see whether I can apply something like interaction term. Right? The other one is if I can add more explanatory variables, so say more independent variables, because it looks like there are different, so my error terms are being explained by something else which I'm missing in my equation, right? You can try all of these scenarios and try to fix this particular problem. Does it make sense? So let's think of
Confusing.
this.
More confusing.
Yeah, that's fine. So let's take this case. So if you remember, we talked about, let's say these are the different sales I'm having.
Uh-huh. Yeah.
Okay. So when I try to see data like this, and for example, let's say I did not build the interaction term. So in that case, most likely I will sort of get a line like this,
Uh-huh.
right? Which means some of my assumptions are going to be violated. It's not going to be having homoscedasticity, and it's again not going to have the normally distributed errors, right? Because you
Yeah.
can say here, so what does the errors normally distributed actually mean?
Mm-hmm.
So normal distribution has two things. One of them is it should be symmetric, right? So
Mhm.
it is likely to have negative errors and it's likely to have positive errors, right?
Yeah.
And the other thing is it's going to be closer to your mean, which means you will have more data points which are near zero and few data points which are away from zero. Does it make sense?
Yeah.
So those are the key things you look at when you talk about normal distribution. Now, if you look at data like this, when you try to see the errors, you would most likely see that there is a high chance of errors being far away and equal chance of errors being close to zero, which means instead of normal, you may get something which is sort of like this. So there is an equally good chance of big errors and equally good chance of small errors. Do you see what I mean?
So you mean the arrow in the first arrow you mean it's look like to change.
Mhm.
It's not such as okay. So you mean the if the more far the one the in the middle points it
Mhm.
feels the arrow is not uh equal than the lower, yeah, the lower
That's what,
point.
yeah.
Yeah.
So that's what you would normally expect in a normal
Okay.
distribution. So
Okay.
for example, if you had a good regression like this,
Mm-hmm.
so then if you try to draw a line like this, then what we're saying is there is small chance of being far away from the line and there is higher chance of being closer to the line, right? Which is what this normal distribution is doing. So you have a great population which is close to the mean,
Mm-hmm.
and the outliers are going to be very small. So you will not have lots and lots of outliers, right? You will have very few outliers, but majority will be close to the mean. Does it make sense?
Yeah.
On the other hand, for a regression like this, because I'm missing the component, because I did not add the relevant variables, because I did not add the interaction term, I will find that my extremes are also very likely.
Mm-hmm.
So this tells me that my normal distribution of errors is not being met, which means now I can use possibly interaction to fix this. So once I use interaction, now I have, say, these kind of graphs I'm making, in which case the individual errors now are going to be much smaller, right? Which means now my distribution of the errors is likely to be more normal.
Okay, so could I repeat your words again? You say you mean in the yeah, if the question is such as if the data is not normal distribute, so we can't to use, and the reason is even though the data we log or we use the interaction to make the data more to be the more likely to be the normal distribution, but
so just a correction.
yeah.
So when you do interaction, that doesn't make the data normal.
Okay.
It tries to make the errors normally distributed.
Okay. So okay.
So when you apply log makes the data normal.
Okay.
But
so,
the other terms I mentioned, like using a quadratic or using interaction or using more variables, they try to make the errors normally distribution. They don't change the nature of the data itself.
Okay.
Does it make sense?
Oh, so you mean we use a log to make the the data normal distribution, and the
Right.
interaction it makes arrows normal distribution. So
Yeah.
even though some data is not normal distribution, but our arrow it's normal. It makes a more normal distribution. It
Yeah.
makes our mean, our outliers to makes more close to the mean.
Yeah.
Okay,
Yeah.
cool.
Makes sense.
To make more close to the regression line.
To the regression line.
Cool.
That is your objective. Yeah.
Okay. It's so clear.
Okay.
Uh,
Do you guys have your test today or is it on Thursday?
Thursday.
Thursday.
Thursday evening.
So you still have a lot of time to catch up.
Yeah, actually in China, we don't have the test in evening.
Oh, yeah.
Yeah.
I found that very specific to New Zealand only.
Yeah.
In fact, I don't remember any other universities where it's very common.
Yeah.
And I think it also depends on the course and all, because I took another course where I think we had it in the afternoon. I think so. It depends on the unit and the department.
Yeah, maybe.
But I think in GSM it's quite common to have in the evening.
Interesting.
Yeah, I think
country.
that's when they do it in the evening, then they have these invigilators available. Maybe that's one of the reasons.
Yeah. And if the finish the test and the lecturer will the check to how to say the checks the test paper and the university cannot give the salaries to the lecturer. So
That would be interesting.
So the business school can get the more money.
Yeah, let's see.
I see the fine. The company.
Hi.
How are you, Param?
Good. How are you?
Good, thank you. Just doing some review. I think I've covered everything. Like I've went through all the tutorials and all the mock tests and everything, but just have a few questions just to clarify some gray areas that I have.
Okay.
For the most part, I understand these, but I want to get a better understanding because when I come to interpret, that's where I get stuck, these specific topics. So one of them is the interaction terms. Okay. So I understand the concept of interaction terms, combining two terms together to sort of get, add a new variable. But my main question is, why would you do an interaction term?
Okay.
I'm sorry if you've repeated.
So I'm happy to do it again.
I'm actually interested in it because I've seen quite a bit of YouTube videos and it seems to be quite common practice to introduce interaction terms, but I really want to try to understand it.
Okay. So let's take maybe we can just do a quick recap of the exercise we did during the lab, or I think it was in one of the tutorials.
Yeah.
Okay. So let's say that let's do it this way. So when I say my y hat is b0 plus b1 times x1. So how do we interpret this thing? So all we are saying is, if this is my x1, then this is my regression line. Again, I'm assuming the dots are all around it.
Okay.
And I know that this is b0 and this slope is b1, right? So this is how I understand this particular term.
Okay.
Now let me add another variable, which is, let's say, b2 x2, and let's say this happens to be a 0 1. So it's like a binary. Okay. So let's assume this is whether you provided training or you did not provide training. Okay. So in that case, I know that if I provided training, and assuming we are trying to predict sales, so the sales may go up. So when I'm trying to look at this, all I'm saying is, in my data, most likely I will have a pattern that looks like this and also another pattern that looks like this, right? Okay. So this is what I sort of see in my data, and I realize that if I try to fit one line, it might sort of go in between them, but it's still not doing a good job, because in reality, maybe this is data for untrained, so this should ideally be the line for untrained, and this should ideally be the line for trained. Do you see what I mean?
Yes.
So if I use this fact, I'm able to do a better job. Okay. So then what I can do is I can say that in this case, I use this B2. So I could possibly say that when x2 is 0, then what happens is I go back to my original equation, which is b0 plus b1 x1. But when x2 is 1, then this becomes 1. So this is b0 plus b1 x1 plus b2.
Yes.
So then I can say this is my b0 and this is my b0 plus b2. But the slope is identical in both the cases, right? So I'm saying the slope is still b1 and b1.
Yeah.
Okay. So now if I try to ask myself, what is the impact of this training in relation to some other variable? So let's add one more item. So let's say we say b3 times x3, and we say this is gender, right? Say male, yes or no kind of thing. Okay. So if we try to apply this, then what we are also seeing is that I may have possibly different lines depending on whether it is, say, male which is trained, this is male which is untrained, this could be, let's say, female that is trained, and let's say this is female that is untrained, right? So I could have different lines like this. Does it make sense?
Yeah, so these are interaction terms, right?
No. So I have not gone to interaction yet.
Okay.
So this is still, so what I'm saying is the slope is still identical in all these cases.
Okay.
Right? So I'm still looking at this being the slope.
Okay.
Does it make sense?
Yes.
Okay. So now I try to ask myself, is there a difference in training being given to male versus female? Right? So if I try to look for that, then what I would like to do is I would like to find, is there an interaction between these two terms?
Okay.
So let's try to develop that and see how it impacts. So let's say I say this is b0 plus b1 x1. So let's say this is the number of hours worked, which I'm not sort of looking at right now. But let me look at this part. So it is b2 times x2 plus b3 times x3, and then I add another term which is say b23 times x2 times x3.
Yes.
So if I see this interaction term, let me see how I can interpret this. So if it happens to be that x2 is 0, which means this is training is not provided, and let's say x3 is 0, which means, so we said this is training and this is male, yes or no.
Okay.
So this means this is
Untrained.
female.
Okay.
Right? So sorry, male is yes or no. So I'm then looking at an untrained female, right?
Yeah.
So x3 is 0, which means it's a female, and training is 0, which means it's untrained.
Okay.
So when I do this, what happens? This becomes 0, this becomes 0, and this automatically becomes 0.
Yes.
Right? So then I get this is b0 plus b1 x1.
Yes.
Okay. Now what happens if training is provided to the female? In which case my x2 remains 0, but this has an impact, right?
Yeah.
So it becomes b0 plus b1 x1 plus b3, because remember x3 is now 1. Sorry, x2 is 1. Did I make a mistake? Oh, sorry, x2 was training. My mistake.
You're right. Yeah.
So all I'm saying is, if training is provided to female, there is an extra benefit of b2, right? Compared to training not provided.
Yes.
Okay. Now let's see, because in both the cases x2 was 0, so I pretty much ignored this term. Now what happens if it's a male that is untrained? So the male that is untrained gets b0 plus b1 x1. So untrained means x2 is 0, but x3 is now 1. So he gets this impact, right? So if you compare between male and female who is untrained, there is an additional impact of b3 for male who is untrained. Does it make sense?
Yes, 100%.
Okay. So now let's ask what happens if the male is provided a training. So this is where this term now has a role, because now both of them are 1. So now what is happening is this becomes B0 plus B1 X1 plus, now I have an impact of B2 and I have an impact of B3 and I have an impact of B23.
Yes.
Now you see what's happening here. Compared to this particular case where a female was trained, there was an additional benefit of B2, right? When a male is trained, there is not just a benefit of B2, but there is an added benefit of B3, B23, right? So this is an additional one that is coming here.
Yeah.
Right? So this tells me that there is a difference in how the training is impacting male versus female.
Okay.
Right? So in this case, so again, I'll just reiterate what I was mentioning in the earlier discussion, is that I'm not saying that training and gender are related. So their correlation could be absolutely 0. Right? So I'm not saying that female is more likely to be trained or male is more likely to be trained. So I'm saying maybe training is provided uniformly. Maybe half of the females are trained, half of the males are trained, and so on. Okay? So there is no relationship between training and gender. Does it make sense?
Yes.
However, there is an impact of training, but that impact is different for male versus female.
Okay.
That is the message we are trying to share.
I'm just writing this down so I don't forget.
Yeah.
Yeah,
So let me do one thing. I'll just sort of clear this up and I will give you another example which might possibly help cement this better. Okay. So let's take this scenario. We have, say, the prediction is B0 plus B1 X1 plus B2 X2, and I add this term B12 X1 times X2. Okay?
Okay.
So now in this case, let's say X1 is the number of hours worked. Okay? And X2 is whether it is female, yes or no. Okay?
Okay.
Okay. So now what we are seeing is, if I'm assuming that as the number of hours increases, maybe the number of sales also increases. So I'm basically expecting an equation like this, right? And so this is going to be B0, this is going to be B1. So every hour worked extra, I get a sales extra of B1. But then there is this impact of female being yes or no, right? So when I apply this, all it is telling me is that if it's a female, then I pretty much have a curve that looks like this, right?
Yeah.
Because this is now B0 plus B2, and this happens to be that my female is equal to 1, right? But you again see the slope is same. Here also I have B1.
Okay.
So all we are saying is, if it's a female, there is an extra sales of B2, but every hour the female works is still bringing me B1.
Okay.
Does it make sense?
Okay. Okay. Yes.
But now let's look at this interesting term. Now here what I'm saying is, if it happens to be a male, which means my X2 is 0, my equation simply becomes B0 plus B1 X1.
Yes.
But if it happens to be a female, now what happened here? My X2 is now going to be 1. So my equation becomes B0 plus B1 X1, same as what we had.
Plus B1 too.
Plus there is an impact of B2, right? And now there is an additional impact of B12 times X1. Do you see this part?
Yes. Yes.
So what is this telling us? That there is an impact on the intercept, which is now becoming B0 plus B2, same as what we saw here. But interestingly, I'm also seeing that there is an impact on the slope. Do you see what I mean?
Oh.
So now what I could see using this interaction term when I try to bring it. So I'm saying if it's a male, then this is B0 and this is B1, same as what we had. But if it's a female, then it has a different starting point, which is B0 plus B2. And now it has a different slope altogether. Now this slope is B1 plus B12. Does it make sense?
Yeah, so it will also affect the model.
Yes. So in effect, what you're saying is, so if, for example, we said this was hours and this was gender.
Yeah.
Okay. So initially we said, if it's a female, she makes maybe another $100 sales. But now we are saying, not only does a female make another $100 sales, but she also makes more per hour.
Okay.
So we said the number of hours has an impact on sales. So that's what we established here.
Yeah.
This part. Right? So now this interaction term is telling us that the gender has an impact on the coefficient for X1.
Okay.
So gender has an impact on how much you earn per hour. Does this make sense?
Yes. Yes.
So the slope itself is dependent on whether it's male or female. So that is a key, I would say, effect of an interaction term.
Yeah,
So
that's what I was trying to understand. It's like, okay, I understand the concept and how, okay, it would differ from one interaction term to another, and you're trying to tell the difference between, let's say, male and female and the impact. I wanted to understand how it affects the model. So I wasn't comprehending that it could potentially make the slope steeper.
Yes. So in this case, what we did was we built an interaction term with gender and let's say hours.
Yes.
So what we're saying is gender not only impacts the intercept, which was this point, but it also impacts the slope itself. Right. Okay. So in this case, this was say X1. So that is a key thing the interaction does. So it is saying, although gender and number of hours may be completely unrelated to each other. So what we're saying is, it's not that males work more or females work more. So gender does not impact hours and hours does not impact gender.
Okay.
However, the impact of hours, that impact depends on gender. So impact is this. This is your impact of hours, right?
Yeah.
So what we're saying is, depending on gender, the impact of X1 itself changes. So that's the key message we want to bring here.
Okay.
Right? So when you say interaction, that is what we effectively might see, that there is an impact of one of the variables, but the impact is different for different scenarios.
Okay.
So in effect, if, for example, if we don't look at this interaction altogether, we might possibly get, say, something like this and maybe something like this. You see what I mean?
Yeah.
So this is how the data might look like. And if you don't look at this part, you'll most likely first try to build a line like that looks like this.
And it won't fit the model very well.
Yeah, again, it might be a poor fit, but yeah, it's still, at least, it's a good starting point. Then you might say, oh, there might be an impact of, say, gender also. So you might possibly build something that looks like this, and maybe something that looks like this.
In that case, that would be the interaction term.
Yeah, so in this case, you still had the same slope, but you said there is a difference between male and female. So there is an impact of gender, but you didn't realize there is an impact on slope also. So again, this model may be a little better than the previous because you included the gender term, but you're not realizing the gender itself is impacting the slope. Do you see what I mean?
Yes.
So if you try to improve this now by bringing the interaction term, then you would say, this is what I would have for one of the cases, and this is what I would have for another of the cases. And then you will see your overall fit improves. Does it make sense?
A follow-up question then.
Yeah.
Okay, let's say I run my regression and I look at my, let's say, male or binary coefficient of male and female, and I see that its p-value is quite large.
Okay.
So it's not statistically significant at that point. And then I run my hours as well, and I see that it's also not statistically significant.
Okay.
Okay, so now I know that my two variables are not statistically significant, right? Okay. But my model has like a good adjusted R-square and a good multiple R, showing that there's correlation between the independent and dependent variables, etc. And my significance F is quite low.
Okay.
Could I argue that introducing an interaction term in this case might help improve the model?
Yes, but I would again say that has to first start with your theory.
Okay.
right? So
If it makes
for
sense.
example, in this case, yeah, so it should make sense that, for example, in this case, we could say that maybe female waitresses who work longer tend to earn more compared to male waitresses who earn longer. So, for example, you could say something like maybe females are still very friendly and so on, even if they work longer hours, but maybe males get cranky after, say, working 5 hours. I'm just sort of making this up. So what you're saying is the impact of longer hours is different for female and male. So if that is your theory, right, then you go to this and build this model based on it and try to sort of see whether it's statistically significant, yes or no.
Yes.
Okay. So I would say the aim is not to just keep on adding different terms and see whether your p-value improves and so on. The aim is to say, what is my theory, what makes sense, and then can I find a good correlation, can I find a good sort of model which is looking at this particular sample data, and do I still get meaningful conclusions? So it is possible that, for example, we definitely say that gender has a role when it comes to maybe there's an impact of pay, but then in our particular model, in our particular sample, maybe the p-value is not significant. Again, it could be that we did not have the best sample, we did not have enough number of observations, or maybe our theory is wrong. So that's also possible. So all I'm saying is, you will not just add variable based on p-value. Instead, you will identify the variable based on your theory, and you will use p-value to assess whether your decision is good enough, or you think it is not justified by this sample. Does it make you challenge your assumption, and so on and so forth.
Okay. Because like one of the examples from the mock test, I had noticed this and I said, oh, this doesn't make sense. Like, why does it have, I know this is just an example of, it doesn't necessarily mean that the regression is correct, but I saw a good multiple R and a good adjusted R squared and a, low significance F. But then I see, like one of the variables, which was online ads, I think, was not statistically significant.
Right.
And then I said, okay, so what if we did like a interaction term to do like, because obviously online ads would be a good indication of income to show if it's, maybe just the sample didn't capture it good enough,
Yeah, but when you say interaction term, what do you think might influence the impact of online ads?
For example, a promotion or...
Oh, okay, wonderful. So what you're saying is, online ads on its own does not mean a lot, but online ads with promotion and without promotion have different impacts.
Yeah, that's what I was thinking. So
wonderful. That's a good theory. So I think now you have a good reason to say that online ads on its own is not a very good explanation, but online ads impact depends on whether it's with promotion or without promotion, and that's what you would recommend as an improvement to the model. I think that makes a lot of sense.
Okay, good. Because I was just checking if that sort of theory makes sense, because I was telling myself, okay, like as a personal, when I see an ad for a company online, I'm not as much to react other than if I see 50% off,
Beautiful. I think that's a very good way of thinking. So again, I would say there are no sort of ideal answers, or there are no sort of yes or no kind of answers that you will have. Yeah. It's more of how do you justify your stance. So I would say focus on that part. So I think what you mentioned is very clear, because you are saying that I think you could just what you talked about, you could just mention that. Like, you see that the customer response to an online ad is different whether it's a promotion or just a regular ad. Right? So that is the reason why you feel that we should take into account the role of promotion with the online ad, which justifies that we should have an interaction term.
Okay.
Yeah, it makes a lot of sense.
Okay, that's great. Oh, you're amazing, Pram.
Oh, no problem. I'm happy that you're able to sort of bring in the right context to this scenario, because I think so. End of it, the aim is not for you to sort of master these tools. I mean, these tools are just to get your actual work done, right? So I think the insight that you brought is actually more important than sort of learning the Excel regression and so on. So I think I'm very happy that you got that part.
I really want to understand it, because I'm doing marketing, and I feel like this stuff is really important to understand.
Definitely. This is like gold. I mean, you can't do any decision making without models like these.
Exactly. So I said, okay, this is like a perfect, and I've never been good at statistics. I've like done it out of memorization before, and obviously, that doesn't get you far. That's why this time around, I promised myself I'd try to understand it so that
Yeah,
I
I'm happy to
can.
hear that.
And okay, sorry, I'm gonna ask. I know I heard you explain it to Tommy a little bit, but I just wanted the only assumption I really can't wrap my head around is the independence of errors. And that's because, so I understand, just correct me if I'm wrong. So we look at the residuals obviously to tell us how good the model is, right?
Right.
If for example our residuals, the sum of the residuals is 0, that tells us that we have a really good fitted line, right? Because everything's sort of around it, and the sum of them are 0, so it's relatively good. If they're randomly distributed, that shows us that there's the linearity is there, and that's a good sign of the actual model if the residuals are randomly distributed and there's no sort of pattern in our residuals. And if we look at our standard residuals versus our y variable, and we see that there's linearity, that's also a good sign of linearity. Okay, and then I understand the histogram is the one for normality of errors. It tells you basically like your residuals are actually normally distributed.
Yeah.
And then homoscedasticity is basically you look at the residual plot and you see if there's any sort of variation in the width of the residuals. So if it's all random spread out equally, then that tells you that there's homoscedasticity, which is good. So I understand those three assumptions, but independence of error.
Okay, the autocollinearity one, right?
Yes, that's the one.
Okay. So let's build on the previous one you said, which is homoscedasticity.
Okay.
So what we are looking at is these are my residuals.
Okay.
And let's say this is my independent variable. Okay. So one of the things I would expect is like a sort of uniform distribution around this and so on, right? So basically what I'm trying to say is I don't see a pattern. So that's the key message I get from here. Okay. So now what happens if this x happened to be, let's say, a time variable? Right? If you remember in the forecasting part, we basically use regression to make forecasts. And how do we do that? We create something like my estimate is going to be b0 plus b1 times my time period.
Yes.
So all I'm saying is as my time goes up, can I predict that my sales are going up or down?
Okay.
Now, let's say I get residuals like this. Now, if I try to plot them over time, so I just try to make a line plot. So let's say I would typically get something like this. So I would ideally expect something like this.
Okay.
Now, what if you have a nice distribution, which is sort of looking random, but when you plot it over time, you see some very interesting patterns, which is like this. So what does this tell you? That every time I'm making an sort of higher forecast, then I do a lower forecast, then I do a higher forecast, then I do a lower forecast. Do you see what's happening?
Oh, so you're kind of, okay.
So there is a pattern.
Yeah.
That every time I do an over forecast, then I do an under forecast.
Okay.
Then if I try to understand this better, then maybe I can get some interesting thoughts. Like, for example, let's say I'm trying to plot this as maybe sales over time, or maybe the number of cars sold over time, over seasons and so on. So what if I finally come to know that, let's say, this is what is happening in summer, this is what is happening in fall, this is what is happening in winter, and maybe this is what is happening in spring.
Okay.
And maybe this sort of gives me some indication that maybe I'm forecasting something which is, let's say, holiday oriented.
Okay.
So maybe this is things that people buy during holidays. So maybe they are not going on holiday during summer and winter, but maybe they are going on holidays during fall and spring.
Okay.
So this tells me that during summer and winter, I'm over forecasting.
Yeah.
But the demand is lower. Whereas in fall and spring, I'm under forecasting, but the demand is higher.
Yes.
Do you see what I mean? So although it looks randomly distributed overall, but still there is a very clear pattern. And the pattern usually is in the form of seasonality.
Okay.
Right? So when you see this autocorrelation part, then what you're saying is what's happening in period 1 is sort of dependent on period 2. Is sort of dependent on, say, period 0. And what happened in period 1 has an impact on what happens in period 2. Right? So when I have this kind of a trend, which I don't see it in terms of the distribution of data. So for example, if I just look at the data, it would just look like this, what I would normally expect for residuals anyway.
Yeah.
Right? But when I try to plot it over time, I see a very distinct pattern. And that possibly gives me a good clue that the autocollinearity is sort of missing here. So there is a clear relationship between once going up and then going down, then again going up and then again going down. Right?
Okay. So autocorrelation is missing in this case.
No, in this case, there is autocorrelation. So in your regression, you want no autocorrelation.
Okay.
Right? But in this case, because of the fact that there is a seasonality and I'm missing that seasonality in my estimates, that is what is causing this error. Okay? So now what happens is, if you remember how we did for the seasonality part, then we added some dummy terms, right? So let's say I do B2 times, I put something like, say, holiday season. Okay?
Yes.
So when I do this, then I would most likely add this component in my estimate, in which case now I will have errors which are pretty random, because now I have taken off the seasonality in my model. Now the errors are going to be more around, did I make a good estimate and then did I fail, yes or no, yes or no. Do you see what I mean?
Okay, so when you add that new variable, you're trying to remove the autocorrelation because your residuals are taking account for seasonality.
Exactly. So now the errors you will get could be randomly above or below. So in effect, what you're saying is you want your errors to be random. But in this case, we saw that the errors are not random.
Yes.
The errors are based on the season. So every time it's, say, the holiday season, I'm making an error. Every time it's not a holiday season, I'm making the opposite error.
Okay.
So once I bring that into my model, now I will get the sort of true randomness. So I have adjusted that, and now I make some errors which are sometimes high, sometimes low, but I can't find the pattern.
Okay.
Does it make sense? So the only difference between what we saw in homoscedasticity, where I say it should look random. In autocorrelation, I'm saying it should look random over time, even when I plot it over time.
Okay.
Right? So this plotting that I'm doing, so I would ideally expect something like as random as this one. So it goes up and down, but I can't say why it is going up and down. I can't find any sort of repeating pattern or anything that consistently goes up or down.
Okay.
So this one has autocorrelation, and this one has no autocorrelation.
Okay, so clear. Okay, that makes sense now. And in terms of like, okay, let's say there's heteroscedasticity. What can you possibly do to improve or remove that? Since now we've gotten into this and you've told me how to fix autocorrelation.
Yeah, so that's fine. So this works both for heteroscedasticity as well as for normality of errors. So I think we discussed this a little before you joined.
Sorry, I apologize.
No, that's okay. That's what this session is for. So one of the things that you can look at is your heteroscedasticity. You have to actually look at the pattern. So let's say we have data that sort of looks like this. Okay. So you can see that there is a trend where the slope is sort of changing over time or over the variable, right? So if I try to fit a simple linear regression, I would get something like this, right? And if I try to plot the errors, you can see that initially I'm making lower estimates, then I'm making higher. Oh, sorry, it should be the other way around, right? Yeah, so initially my residuals are negative, then they are positive, and then they are again negative. Do you see what I mean?
Yes.
So I can see there is some pattern. Ideally, I want no pattern. So this tells me that most likely this line is not the best fit. Okay. Now, what if I try to fit a quadratic, which means I go something like this? You see what I mean?
Yes.
So when I fit this quadratic, now I'm trying to measure errors against the quadratic. then it is more likely that I will have an even spread. Sometimes I go under, sometimes I go over, but I don't see a trend. Does it make sense? So one of the options is to improve your model by applying your quadratic term.
Okay. So I think I got this from caught you in Tommy's last.
Okay. Yeah. So
you're saying
again,
quadratic is for the residuals, so not for the actual data, right?
No. So the residual should be randomly distributed. So this homoscedasticity that we are talking about is for the residuals.
Okay.
So what we are saying is, if you build a quadratic model that is a better fit, then you will see that your residuals are more likely to be randomly distributed.
Okay.
Does it make sense? So this is one of the things you can do.
Sorry, just the graph on the left, the one where you've put the quadratic.
Yeah.
Sorry, to the left, where you've done the line of better fit. Yeah, that one. Yeah. So that's for the data or the residuals?
So this is for data. So this is
data.
Y.
Okay.
This is X and Y. This is your residual over X.
Okay.
And your quadratic term is going to be this one.
So your quadratic term helps to sort of give that curvature, as we saw.
Yes.
If a B1 coefficient is positive, B2 coefficient is positive, it looks like it's going upwards, a positive. Okay, okay, I understand that. Okay, now I see.
So again, so you can use quadratic if you see a slope which is sort of tapering over time, or tapering over the x-axis. So it could be something like, maybe if you keep driving more, you will earn, say, more per kilometer that you drive. But again, eventually, if you drive, so going from, say, 1 kilometer to 2 kilometer, that difference versus going from 100 to 101 is not going to be the same.
Yes.
So when you have scenarios like this, you can think, is there a slope which is decreasing over this particular variable? And that could be a possible case of quadratic.
Okay.
So let's take another scenario where we had data like this, and then we had more of these sort of extreme points going far above and so on.
Okay.
So let's say this was Y, and then we are basically seeing that if I try to fit a line, then I go something like this, right? And if I try to plot my residuals, again, they would look maybe opposite of this. So they don't seem to be scattered properly.
Yes.
And this tells me that looks like I have a lot of these errors which are not uniformly distributed. And if I try to look at the distribution of Y, it seems to be having this long right tail distribution. That's why I'm having more extreme values of Y as it increases, right?
Yes.
So this possibly tells me that maybe I can try to sort of do a log, and by doing log, I'm sort of compressing this whole thing downwards. You see what I mean?
Yeah.
And in that case, maybe after doing log, I may possibly have these terms which are going far above come closer to this and possibly have a closer to a line fit, right? So doing log is another way. So again, remember that these trick work. So if you're able to find the right thing to do, you can in fact handle all of them in one go. So for example, if you remember, one of the things we were expecting is linearity. So when I do this, it's sort of looking non-linear, but when I do this, it sort of handles the linearity part. When I do this,
because it squishes the data together, so you can get more linear.
Yeah.
Okay.
So same way, by doing this thing, by applying log, not only did I solve my linearity problem, but I've also solved the homoscedasticity problem.
Okay, that makes really good.
Yeah.
So basically,
because I did, sorry, just to complete, because I did this, I'm also now handling the normality issue. Because remember, we said the error should be normally distributed.
Of course, yeah.
Right. So a lot of times, applying one of the corrections can handle 2 or 3 things together.
Nice. Okay.
Yeah. Sorry, go ahead. You were saying something.
So basically, a reflection of your assumptions all starts with how your line is best fit in the beginning.
Yeah.
So basically, That's why we do things like quadratic and logarithms, is try to get the best fit lines. So usually if we have the best fitted line in the in the start, that would increase our chances of having the assumptions that we want in the end.
Yes, but again, that's being very idealistic.
Of course, yeah.
Unless you're dealing with, say, engineering systems, it's very difficult to get a line of best fit in the first go, because it's not like temperature is related to pressure and I'll get a very nice fit all the time. Because most of the time in real world you don't have, because in the physics or in the engineering side you have true equations and you're just seeing random observations with some errors. Whereas in real life there are no true equations. Right, so you're trying to build an equation to model that real system, but there is no, I would say, there is no physical law that says what is the impact of gender and training on sales.
Of course,
it's a social impact, right? So that's the reason why regression models will not have very, very high sort of predictability and so on in the real world.
Okay.
So I talked about quadratic, I talked about log. The other thing you can do is, maybe when you're looking at data like this, you may see that you're not accounting for some other variable that is explaining some of the deviation, right? So you can add another variable. So let's say earlier you had b0 plus b1 x1, and you had a lot of errors which were possibly related to the impact of x2.
Yeah.
Right? So in that case, you can see that maybe adding x2 can possibly give a better explanation, and adding x2 will also make sure that your errors are coming down and they are getting more randomly scattered. So adding a new variable may also be a good way of handling homoscedasticity as well as normality errors.
Okay.
And the last one is the interaction terms. So if you remember, we talked about like this kind of scenario and this kind of scenario, so where the slopes themselves are different. So if we did not include the interaction, what would we do? We would do something like maybe this for male and possibly this for female. That's the best thing we would do, right? And in this case, when you try to plot your errors, you might see that as your x is increasing, your errors are sort of scattering upwards and scattering downwards. Do you see what I mean?
Yes.
So you have more of errors going this way as x is increasing. So again, this might tell you that there is a potential interaction that you're missing. And when you put the interaction terms, then you get like these lines and these lines, and then your errors are going to be more normally distributed. And your homoscedasticity, like your errors are going to be more randomly distributed, and they will be closer to a normal distribution.
Okay, so it goes hand in hand with improving the model.
Exactly. Yes, you're right. So that's the reason I said, mostly if you are able to find the right things that are impacting your model, you would be able to improve your adjusted R-square. You will be able to get reasonably good coefficients, have reasonably good p-values, also handle all the assumptions in the right way.
Okay.
Does that make sense? But again, it's not like, I won't say it will happen all the time, but if you start with a good theory and collect your samples in a right manner, it is very likely that you'll be able to address some of these in, like, if you go step by step.
Okay. And just one last question I have. Yeah. So thank you so much for clearing that up, because that now put such a nice picture to everything.
Okay, happy to hear that.
The last question I have is that, for example, if you have what appears to be a good model, by looking at your standard, so just to clarify, so to assess a model, you would first look at your multiple R, right? To check if there's correlation between your independent and dependent variables.
In fact, you can start with adjusted R-square, because multiple R and adjusted R-square are very highly related to each other.
Okay.
So let's say, again, this is nothing for the exam, but just to let you know, your multiple R, and if you square that, you get your R-square.
Okay.
And on the R-square, if you apply a term that is based on the number of variables you are using, that is how you get adjusted R-square.
Okay.
So if you just look at adjusted R-square, it allows you to sort of make the prediction right away instead of looking at 3 variables.
Okay. So the way that I usually go about it is that I just go in order. So yeah, I'll look at the adjusted R-squared. Okay, looks good. 0.6, let's say. explain some variability in the data. Then I'd look at my multiple R. Okay, it's greater than 0.7, gives me a good indication of the model. And then I also look at standard error to see if it's high or low, to tell me, okay, how far are the residuals from the line.
Yeah.
And then I'll go to my significance F. I'll see, okay, I have a low significance F. That's great. It's showing me that the model is significant and that it's existing model. And then I'll look at let's say my p-values, okay? And I noticed that, because this was one of the examples in the mock test, I look at it and I see all my p-values are not significant.
Okay.
So I'm like, okay, now I'm stuck, because like everything looks good, but my variables aren't significant.
Right.
So is this where I would introduce something such as logarithm or quadratic? Because obviously I can't plot the data and look at the scatter plot.
So if you don't have the actual data to look at, then you can just make these assumptions in your explanation. So for example, you could say that once you look at the data and you see a non-linear trend, you can apply a quadratic and maybe improve the model. Or once you look at the data and you see a right skew, you can apply a log and try to see whether that improves. So since you don't have access to data and you can't do these calculations during the sort of when you're answering the test, you have to sort of give your justification for what you might want to do in order to achieve something you want to achieve. Does it make sense?
Yeah, okay. So you would recommend that I introduce the if I had the data, blah, 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 then I would do this. If I had the data, blah, 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 then I would do this.
So as far as the model as it is concerned, I would then ask, do you see that there seems to be a good theory which links the variables mentioned to what you're trying to predict? If yes, you can still continue as long as you sort of make it clear that the p-values are above your cutoff limit.
Okay.
But so you're still saying that the model makes sense to me. The only thing is the model is not having coefficients which are statistically significant. So that is more like a disclaimer.
Okay.
See what I mean?
Yeah.
So all you're saying is, this is a model which I think makes sense, but use it with caution, because based on the sample that we have collected, it does not seem to be statistically significant. So just be aware of the fact that we might need either maybe more sampling or some better corrections to do later. But the theory says that this makes sense.
Okay.
Right? But if your theory itself is that, I mean, you don't see any relevance why you should add this particular variable, then I think you can argue right away saying that the model doesn't, I mean, the variable itself is not a good predictor in general. Plus, you see that the p-value is much higher than, say, 0.05. So you might recommend removing this from the model and trying to do the regression again.
Oh, okay. Yeah, that's someone I didn't think about. Okay. So yeah, maybe I look at some of the variables, like if they're talking about, let's say, sales, and they have sales of cars, and all of a sudden they have the weather as a variable. I can be like, oh, how does, like, that doesn't add much meaning. So maybe removing it would improve the p-values of the other variables.
Yeah. Okay. That will work for cars, not for umbrellas.
Yeah. 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 Okay, I get it. So first thing you do, you think I should like first thing you recommend I do is test the logic of the model itself.
Yes. So I would say first thing you do is write out the equation.
Okay.
So you say sales is equal to whatever 5,000 plus 300 times the weather plus 500 times the temperature. So first write out the equation. So once you write it, that actually gives you a good clue that what is the model telling you, that for every degree increase in temperature, the ice cream sales goes up by $500. This seems to make some sense.
Yeah.
But for every degree increase in temperature, the car sales goes up by $200. That doesn't seem to make a lot of sense.
Yeah. Okay.
You know what I mean? So you can, when you write out the equation, you can then start to build your justification saying that, does this seem to make sense? And again, the thing that we were talking with Tommy as well was, you also have to see whether the coefficients are meaningful. So if you have a coefficient that's extremely small compared to the other ones, that's not really adding a lot of value to your model. So you get something like, if the temperature goes up by 1 degree centigrade, your car sales goes up by 25 cents. So even if the p-value is say 0.001, so 25 cents increase in sales of car is significant, but what do you do with the information? I mean, if you increase your car sales by 25 cents, you can't do anything with the model anyway, right?
Yeah, that's true. Yeah.
So you can also comment about whether the coefficient is sort of meaningful from a business perspective that you can use for your predictions and so on.
Okay.
Right?
So not even if it's statistically significant, but it's such a small amount compared to other things, then why introduce it?
Exactly, because you're just adding complexity and you're not adding any value to yourself.
Sometimes simple is better, right?
Exactly. Yeah, I mean, I would say regression simple is always better.
Yeah.
So see, ideally, I would say in real world, if you have say more than 3 or 4 variables, it's more of an academic model. It will never be used in real life. So it's good for writing papers, but it's not actually good for doing business.
Okay.
Right? So just keep that perspective in
Sometimes
mind.
you get caught up in all the numbers and stuff. You forget about the logic. It's like you have to actually test the logic. Does it make sense? What are you exactly trying to find out? Are these variables adding value? Like, are there coefficients adding value? Like, and sometimes I forget that side of things, like to test the logic, not just the numbers, you know, and p-value, significance, blah, blah, blah.
So I normally find that if you just write out the equation,
okay, that's
like just saying that, okay, sales is equal to this plus this plus this, that gives you a very good understanding of what is it that I'm actually trying to do and how much value does it add. And in those cases, you might normally see that putting those 5 decimal points in your coefficients and p-values don't really add any value. Right? So if you're trying to predict, say, car sales, so going below a dollar amount does not really make a lot of sense. You see what I mean?
Yeah.
So you can just keep that perspective. So that way you'll just make the equation simpler for you to analyze and comment on.
Param, I really want to thank you so much. Honestly, you're a great teacher.
So that's so nice of you to say that. I'm happy to help.
We're so lucky to have you. Thank you so much. Honestly, you've helped me so much.
No problem at all. Happy to help.
Thank you
okay,
so
I don't
much.
want to take up any more of your time. Tommy, I'm sorry I took up so much time.
No worries.
You have any more questions?
I don't have any questions. Yeah.
Oh, okay.
I just listen your questions and I find we have the similar questions. Yeah.
Okay.
Yeah.
Good.
I think that's a very good use of time, right? Like just listening to each other's questions and explanations.
Yeah.
Well, thank you so much, Param. I really appreciate it.
No problem. Wish you all the best.
Thank you so much.
You
have a good night.
Thank you. Bye.
Bye. Wish you have a good day. Thank you.
You too. Bye.
Bye.